So for this project, we have decided to do problem 2, which includes two different masses. So we have mass B and mass R, and we have two springs, which are identical to each other. This means that they are the same length and they have the same spring constant. In this problem, there is no friction, and both of the objects start from rest. So in this problem, it starts out by mass B compressing this first spring, and then mass B is shot forward by the compressed spring, where it collides with mass R. And this collision is perfectly inelastic, which means that these two objects stick together. And they both continue forward at the same velocity, and at the end of the problem, they both run into the second spring, which compresses this spring until both of the objects stop, and this spring is compressed as far as it will go. Now, the object of this problem is to find x final, which is basically the displacement of this final spring from the spring's equilibrium, so where it is naturally, and the length it is when it's compressed. So to calculate this problem, we need, first we need the equation for the potential spring energy, and we also need the law of conservation of energy, which basically means that all of the energy within a system is always going to be the same. Like, it's always going to be constant. And then we have the work energy theorem, which is basically just the change in the energy that's in a system, so whether a system loses energy or gains energy. And then we have our equation for work, which includes force. Now for this problem, our system is going to include both of the masses, so mass B and mass R, as well as both of the springs. And this basically means that there is no external force being applied to this system. All of the forces are internal, which means that you can plug 0 into this equation for work, which basically means that the net work external is equal to 0, and this means that the energy within this system is conserved. So for this problem, we only need to be concerned with potential energy because at the start of the problem, all of the energy is potential, and at the end of the problem, we will end up with our max potential energy. And this also means that the spring here is compressed as much as it will be for this problem, which is what we're being asked for. And in order to find this, we need to find the change in energy, which would equal 0. And the way we do this is we have the equation for the final energy, which includes the x for this spring, subtracted minus the initial energy, which is the energy for this spring. And when you do all the algebra, you find that these two springs are compressed the same distance.
Alright, so for this problem, from our solution, if we think about units, the spring constant has units of newtons per meter, or newtons divided by meters. And then we know that any displacement or distance in the x direction is going to be in meters for this problem. And then energy is newtons times meters, or joules, but that's what joules is equal to. So for specifically this problem, when you multiply the spring constant by the displacement of the spring from equilibrium squared, the meters will cancel out on the bottom and it becomes newtons times meters, which is energy, which checks out. So that means that this equation theoretically checks out. So when solving for our symbolic answer, you have the newtons per meters of the spring constant, and then the same spring constant because both springs are the same. So when you divide over, these newtons per meters cancel out. You're just left with meters squared and meters squared. And then when you take the square root of that, the meters squared becomes just meters, and now you have meters on both sides, which makes sense, and that checks out. Now, for covariational reasoning, we have both of these are affected by each other, and since they're equal, it's basically saying that as x initial, or the displacement of the spring at the beginning of the problem, gets bigger, the final displacement of the other spring gets bigger. And this makes sense, because if you put a lot of force and a lot of and create a big displacement in the spring, it's going to shoot an object farther, and that's going to, if it collides with another object so it stays together, it makes sense that that would also compress the spring a pretty large amount. And then a special case analysis, if the initial spring equal compression is 0, that means that x final would be 0. And that makes a lot of sense, because obviously if it's 0, that means there's no compression, there's no force from the spring, there's no outward like kinetic velocity or anything pushing or moving the object, so the object stays at rest and nothing happens, and nothing will happen to the spring because it won't get compressed if everything stays at rest.
After our calculations and making sense of the results we've received, we know that the spring final is going to be equal to the spring initial when both the boxes come in contact with the springs. There's also no more kinetic energy involved after the boxes come in contact with the spring because they're not moving at all, so that means no kinetic energy is involved anymore in the system. Potential energy would be at its maximum at the beginning and at the end, since we're saying that the spring is being compressed the same amount at the beginning or initial and the final points. To compare and contrast, we have an example that we used in class with the racquetball and the basketball. So Paul dropped both of the balls at the exact same height, so that's a difference between the two, because our boxes start at different locations. In the example, one box is started compressed on the spring at the beginning, and one box is started with no movement at all in the center of the system. Although both situations, the distance is being measured, and the spring compression, for example, is the distance that the spring is being compressed, and then the distance of the height of the ball as it bounces back up. For both of these systems, we can ignore kinetic energy because potential energy is at its highest at the beginning and at the end of the system, and that's what's most important and what we're looking for. We also know that both problems are looking for potential energy at the maximum point because that's when the spring is being compressed, and that's what we're looking for. And then another difference we have is that the ball problem involves mass in its potential energy, but the box problem does not, since both of them have different masses. And then another difference we have is that the ball problem has maximum potential energy at its maximum height due to the racquetball being flung back up into the air after bouncing off of the basketball, and that creates its maximum potential energy since it's not moving anymore, since there's no kinetic energy. But with the box problem, it has max potential energy when the spring is compressed, which is at the beginning and the end of the system. And then we chose to do another problem from Studio, which was problem 9-2. And the problem that we are doing, as well as the problem done in Studio, are very similar because they both involve two boxes, one at rest and one moving in a rightward direction. So that's a similar attribute between the two. Both boxes have different masses, so that's also similar between the two. problems. And then for our differences, after the boxes collide, they bounce off of each other in problem 9.2. But in our problem, they stick together, and this is due to the differences between an elastic and inelastic system. Our problem is inelastic because the boxes stick together, and that makes it perfectly inelastic. And then the problem from Studio is elastic because they don't stick together.